Record, share. Sekejap ah. Tiba-tiba disconnected pula. Hmm. Hmm. Okay, let me share again. Oh, ada participant coming. Okay, hold on. Okay, all right. Okay, can you see the slides? All right, good. So let's move on. We've started to discuss about PN junction yesterday. And so let me just recap. Right, PN junction is formed when we combine a p-type semiconductor material and an n-type semiconductor material together. And when you talk about this PN junction, we're going to talk a lot on homojunction, which involves formation of a junction between the same material, the same semiconductor material of the same crystalline lattice and also band gap. Okay, and later on, we're also going to look into heterojunction formation, where we are going to combine different materials as a junction. So one material as a p-type and one material as an n-type, right? So for example, if you talk about crystalline silicon to crystalline silicon PNN, we call it as a homojunction. If you talk about crystalline silicon to amorphous silicon, it is a heterojunction. If you talk about crystalline silicon to zinc oxide, of course, it's a form of a heterojunction. Okay. Yesterday we have discussed about what happens to the PN junction when we combine the two materials together. And before this, we have learned that the p-type material is made of holes as the majority carriers and electrons as the minority carriers. And n-type semiconductor, on the other hand, is made of electrons as the majority carriers and holes as the minority carriers, right? So the majority carriers is given by the doping level that we use. So you can approximate your P to be equal to Na, for example, and N to be equal to Nd, because we have been assuming 100% ionization of the impurity atoms in the lattice. So to be able to get the minority carrier concentration, you can just use the law of mass action, N times P equals to Ni squared, in order to know the concentration of the minority carriers, right? So the moment we combine both P and N materials together, just let me see that. P and N semiconductor together. So what's going to happen is the majority carriers from p-type, which are the holes, are going to diffuse into n-type materials. And at the same time, we're also going to have majority carriers in the n-type material, which are the electrons, going to diffuse, right? You can see this, going to diffuse into p-type material due to the presence of concentration gradient. And due to the diffusion, we are going to have depletion of carriers near the p-n junction, right in the middle of this schematic, right? Near this central region, if you like. So you can imagine this as this region near the center, the metallurgical junction, and this is the region away from the center, right? So due to the diffusion of majority carriers, electrons and holes, the central region is going to be depleted of both carriers, and they are called, and it's called depletion region, right? Depletion region, because the region is depleted of carriers of both polarities. On the other hand, the region on the left hand side is going to remain neutral p-type lah. So because we have now p-type on the left, semua ni p-type dan semua ni n-type, and this region to the right is going to be neutral as well. So the region with space charge is going to be the central region, right? So this one are the negative space charge on the left and positive space charge on the right. Okay. Due to the diffusion as well, when thermal equilibrium is reached, we're going to have electric field that is set up across the junction, and we're also going to have VBI, or built-in potential, that is going to stop both carriers from further diffusion into the neighboring region. Right? At that point, the diffusion of both carriers will stop. Right? Haziq, depletion region, band gap. Okay, depletion region is not the band gap. Band gap is band gap, just like what we discussed before. Band gap is always given by EC to EV. So we're gonna look later on. We're gonna go through how is the band diagram is going to look like in a p-n junction. So before this, when you talk about so this is the band gap, EG. So before this, we learned that when you talk about n-type semiconductor, you're going to have band diagram like this, right? Fermi level close to the conduction band H. And on the other hand, if you talk about p-type, we're going to have EF close to VB or EV, right? So soon, we're going to see what's happening to this original band diagram when we combine both materials of opposite polarities in a p-n junction. Okay, we're going to come to that, right? But a depletion region is not band gap, right? Depletion region is the central region, central physical region, if you like, physical region. When you combine, say, if this is your silicon wafer, for example, if you start off with a p-type silicon, you are looking at a cross section now. And let's say you are diffusing an n-type on top of a p-type silicon. So you have a very thin layer of n-type on top of this p-type. So part of the wafer is now n-type on the surface, and then the region below to the back is all p-type as the original region. So the depletion region is the region near the junction. Is a very small region, right? So it can be calculated, and but it's small in nature, right? It's very, very small. And that's not band gap, because they are two different things. The depletion region is the physical region depleted of both carriers due to the diffusion of hole as the majority in p-type and diffusion of electron as the majority in n-type into the neighboring region due to concentration gradient upon combination. Okay, so depletion region is the depleted region. Band gap is the band gap, right? The distance of between EC to EV, which gives the intrinsic properties of the material as the one that we discussed before. So we're going to come to that later on together in a schematic of a p-n junction. So we'll come to that, right? So this is what happens when we join a p-type silicon and an n-type silicon, or it can also happen to some other material as well. So we discussed yesterday that the majority carriers in p-type is going to be given by Na, or also equals to pp naught, right? Three things you have to describe here. Pp naught, density of holes in p-type material at thermal equilibrium, and N naught is density of electrons in n-type material at thermal equilibrium. Okay, so this is both in p-type and n-type, right? So this is the majority. So if you want to look at if you want to look inside a material, then you have to look like this in a bracket, right? So the top one is the majority, pp naught. As a result, the minority is the np naught. Okay, atas majority, bawah minority. Majority carrier, bawah minority carrier. Okay, so majority is given by pp naught equals to Na, and when you use law of mass action, the minority will be given by Ni squared over Na, or Ni squared over pp naught, right? On the other hand, it's also true for n-type material, where the majority is up here. Majority is given by Nn naught or Nd. Therefore, the minority is given by Pn naught, and is equal to Ni squared over Nd, or Ni squared over Nn naught. Okay. So if you look at the illustration down here, if you look at the p-type material on the left, p-type on the left and n-type on the right. So the majority carriers in the blue region, in the blue material, are holes, right? You can see more of positive mobile charges. So they are all mobile charges, yeah? Mobile. That's why they move. Mobile charges. They are not fixed charge. Fixed charge is the result of atoms being left without electron or without hole, right? So that's a fixed charge. But this one is mobile charges. Yang bergerak, fixed charge doesn't move. So this is the majority, and you can also get your minority here. So if you look at these positive charges, positive, so they will make the pp naught. They will make the pp naught value. And at the same time, you're going to have your minority, which will make your np naught at thermal equilibrium condition, right? So the same goes to the n-type material, where you can see a lot of electrons, so a lot of negative charges, mobile as well. So this Nn will be the Nn naught, the majority carriers as well. And this small number of minority, the positive mobile charges, will be the whole as the minority carriers in n-type, and that will give you the Pn naught. Okay, you have to be clear of this, okay? Because the moment we'll see later on that they will move across, and the moment they move across, they'll become the concept of minority carriers will be more important. Okay, so now what you see in this blue region and the red region is the carriers in the original material, right? Carriers in the original material. Maksudnya dia belum ada diffusion lagi, ya. So now if you look at the blue region, the majority carriers are holes, right? Betul. Okay, agree with me? Agree with me? Majority carriers are holes, right? Betul. Okay, clear? Right. So these holes in the blue region, so remember when you join the P and N, the hole will diffuse into N-type, right? And the electrons will diffuse into P-type, right? The opposite region, right? So the moment holes diffusing into N-type, they are started in P-type, right? You have to be clear of this. Originally from P-type, now it's diffusing. Holes are diffusing into N-type. When holes diffuse into N-type, the holes will now become minority carriers. So originally in the P-type, holes are the majority carriers and electrons are the minority carriers. Sekarang ni, holes are moving into the N-type. Holes now become minority carriers, no longer majority carriers. Macam you orang Malaysia lah, okay? You orang katalah you Malay is the majority, right, in Malaysia. So you are the majority in this country. But the moment you migrate to UK or Poland or Russia, You are no longer the majority, right? You're no longer the majority in Russia. You now become the minority. So the same concept applies here. So the moment you cross into the neighboring region, neighboring country, for example, for the sake of understanding, you now become minority, even though you were originally a majority in the original material. The moment the holes are now in n-type, due to the diffusion, the holes now become minority carriers. And the same goes to the electron as well. Electrons were the majority carriers in n-type, but the moment they diffuse into p-type, they now become minority carriers. So you have to be clear of this, because we're going to do a lot of calculations on the minority carriers in the opposite material. Okay, so if you're confused with the majority minority in the original or in the new region, you will be confused with which values to pick, right? When you do the calculation, then you're going to end up using different values, and then you're going to end up doing different calculation and end up with different answers. Okay, holes originally majority in p-type becomes minority in n-type. Electrons majority in n-type becomes minority in p-type. Clear? So now let's look at this. Alamak, kejap dah 1.40 dah. Saya dah kena masuk 145. Okay, Rafai said, so hole from p-type diffused to n-type, so the diffused hole will become minority and n-type. Yes, exactly. So hole asalnya dari p-type kan, sebab dia majority. So what will diffuse? Okay, let me just get this straight, at least for this class, before we move on. Daripada you tak clear and we proceed, might as well we get everything okay first. Hole is the majority in p-type. So what will diffuse upon combination of P and N is the majority carriers. So we're going to look into majority carriers diffusion only. Okay? Because we see concentration gradient, right? So hole terlalu banyak in P-type, but so little in N-type, because N-type pun ada minority carrier hole kan? But then hole is too much, if you like, in P-type and so little in N-type. Therefore, holes diffuse into N-type. So the moment holes diffuse into N-type, when it reaches N-type, the holes will become minority carriers. Sebab originally dalam N-type dia kan minority carrier kan? Cumanya the magnitude is not a lot lah, because we do the law of mass action calculation. Let's say the majority N-type is 1016, therefore the hole be only like 10 to the 4, right? Which is so little in comparison to 1016. But due to the diffusion of new holes from the p-type, dia akan masuk ke n-type. So you're going to have like new minority carriers. The number of minority carriers will increase in n-type region, and the number of minority carriers will also increase in the p-type region due to diffusion of electrons into n-type. Okay, is it clear, Rafai? What will diffuse is the majority. As a result, bila majority cross, dia akan jadi minority di seberang, right? Macam konsep tadi, you are Malay in Malaysia, for example, which is the majority at the moment, but tapi kalau pergi Australia, then of course you'll become minority, right? Because there are bunch of Australians, millions of Australians over there, and you'll perhaps form 100 or 200 of Malaysians in Australia. So you become minority in Australia, but you are the majority in Malaysia. Okay? So get that right first. Kalau you tak dapat itu betul, nanti when you plug in the calculation, you're gonna pick up the wrong thing. Okay, let's go through for another 5 minutes. Saya perlu join the workshop. I'm sorry for that. Gradient in carrier concentration at a junction give rise to diffusion flow of majority carriers, right? So we learned before in carrier transport phenomena that whenever we have concentration gradient, we're going to have diffusion of carriers to the lower concentration sites. Okay, macam kita baca teh kan, teh bermula dari uncang, where it's going to be dissipated across the hot water, because dalam uncang tu is the high concentration region, and the rest of the hot water is low concentration region, and therefore the tea dissipates or diffuses into the whole region to form thermal equilibrium. So the moment you form the hot tea, you can see the color is uniformly distributed. You already got thermal equilibrium condition. Okay, the same applies here. The moment you have diffusion of holes into n-type, electrons into p-type, at some point it's going to reach thermal equilibrium. Macam teh. Bila teh dah siap, dah rasa manis, dah rasa teh, thermal equilibrium, right? So gradient, due to concentration gradient, we're going to have diffusion of majority carriers. Holes will flow from p-type into n-type. Okay, you can see the arrow here, blue arrow, which shows holes diffusing into n-type. And we're also going to see in the next slide electrons diffusing into p-type, right? So if you want to imagine, if you want to translate this into a graph, for example, you can see this below graph where you can plot the majority. Remember, majority is the PP naught, right? PP naught. Revisit this, the previous slide. This PP is actually PP naught equals to NA originally, right? Originally, keadaan asal. So it's plotting the concentration of the carriers, in this case the holes, against distance on the x-axis, right? So the left-hand side, the first half of the graph is about p-type, and the second half is about n-type. So due to the diffusion, we can see that the concentration is abruptly reduced at the junction. Katalah ni dekat junction lah, lebih kurang tengah lah. Due to the motion of the holes into n-type, we're going to have diffusion current density due to holes. Okay, so previously we have learned about diffusion and drift component that belongs to holes and electrons. In this case, it's just about diffusion of current density due to the movement of holes into the n-type, right? And that is given by negative QDH dP dx, right? Just like our previous equation that we learned in carrier transport phenomena. And the region near the junction becomes depleted of carriers, okay? So depletion region here, Haziq is now, you ask about this depletion region. Depletion region is referring to this central region near the border of P and N, right? This is the region where the carriers are depleted. But you can imagine like most of the carriers that are diffusing into the neighboring region come from the central region near the junction, right? So that's why that region on the left-hand side, on the right-hand side, becomes a depletion region, right? So the junction becomes depleted of free carriers, therefore it's called depletion region, leaving behind fixed ionized dopant atoms, right? Fixed ionized dopant atom. Fixed is not mobile, okay? Mobile, if you talk about mobile carriers, it's referring to the electrons or holes that are diffusing. But in this case, it's referring to fixed ionized dopant atoms. Tak bergerak, So due to the atoms, what we call losing electrons, atom kan kalau dihilang elektron dia akan jadi positively charged kan, and on the other hand it's going to be positive negatively charged, right, if it receive electron. So the same thing happens here. So this region is about fixed ionized dopant atoms, right? So and the neighboring region dekat tepi-tepi ni is all about the mobile charges. Okay, don't be confused between mobile and fixed charges. This depletion region supports an electric field between the positive and the negative fixed charge. So we're going to have electric field set up across the positive and negative fixed depletion region, fixed atoms yang ada dalam depletion region. So you're going to have electric field set up across the fixed ionized dopant region, but you don't have any electric field in the neutral region to the left and to the right. Okay, the field collects minority carrier holes from the N side. Okay, so apa akan jadi next is when you have the fixed charges set up across the junction. So note that here, before we move on, note here. So the N-type region, the N-type semiconductor with electron as the majority, is going to have positive fixed charges, while the P-type, which originally has holes as a majority, is going to have negative fixed ion charges, right? Fixed ion. Maksudnya dia punya fixed ion tu is going to be the opposite properties as the original polarity of the semiconductor material. We know that P-type is positive, but in the depletion region, the charges are negative in nature. And we learned that N-type is negative, therefore the depletion region for the N-type will be positive in nature. Okay, note the opposite sign here, right? as a result, 41 tu apa? Haziq? What is 41? What do you mean by 41 there in your chat box? Kucing? Apa tu?
Tadi ada kucing lalu atas saya punya board. Sorry datang.
Ah, okay. Alright, okay, that. Okay, so selingan lah, okay. Saya tak nampak dia punya gambar tadi. Okay, I'm rushing to finish. Okay, so as a result, right, the field collects minority carrier holes from the N side, right? Minority carrier, if you look at this, minority carrier holes from the N side, this is the minority, right? So due to the presence of the electric field and negative charges in depletion region, this minority will be attracted to cross the junction, right? The field collect minority carrier holes. So this is the minority carrier holes in the N-type. Will be attracted, will be withdrawn by the charges, by the force due to the charges in the depletion region. Negative ni akan tarik, negative ni on the left will attract this positive to cross the junction. Okay, that is the result of the presence of the electric charge in the depletion region, right? So the same thing happens to the minority carrier electron in p-type as well. It will be attracted by the positive charges in the depletion region to cross into the n-type region. Okay. So here you can see that if you want to plot again the pp naught against the distance, so you're gonna see two different currents due to hole, right? Two different currents due to hole. First one is the diffusion current that we discussed in the previous page, given by negative QD, dep, dx. And the second current is given by this withdrawal of, or attraction, if you like, of the minority carrier hole in n-type to cross the junction to go into p-type. And during the movement, we're going to have a drift component due to this movement, and that will be given by J drift, and it's going to be given by the equation that we learned before, Q P mu H E, right, due to the presence of the electric field. Okay, so the same thing is going to be seen in the p-type for the electron as well. So this is only for hole, and you're going to have the very same thing for electron as well in the next page, right? So you're going to have a drift component due to the drift of electron, minority carrier electron into n-type due to the presence of the positive charges near the junction that can tarik negative, right? And also due to the diffusion just now, we already have the diffusion current density, which is given by QD, dn dx, right? So this is due to the electron, and the previous page is due to hole. Okay, I'm just going to stop here first. Next week we'll recap on this if you still don't understand, and we'll move on to the next thing, which is the PN junction. See, this is on this page. You're going to see later on, when you combine the Fermi level of n-type and p-type, what is going to happen in the PN junction, right? We're going to see some banding of the valence band and conduction band in order to align our Fermi level in both materials, right? So upon thermal equilibrium in the PN junction, we're going to have only one level of EF. Kita mula-mula EF in n-type is close to the conduction band, and EF is p-type is close to the valence band. Kalau saya boleh letak macam ni ya, if just I would like to give some comparison, n-type kat atas ni close to valence conduction band, and EF or p-type is bawah ni close to valence band. Upon combination of PN junction, this EF is going to be aligned, and as a result, your conduction band and valence band will need to bend accordingly in order to accommodate a single Fermi level at thermal equilibrium. Okay, so is it okay so far? Saya tak boleh nak entertain any question at the moment because I need to run back to the workshop, and I'll see you again next Monday. Okay, so is it okay so far? Sorry for today, I need to rush because the workshop is full day. Luckily, I don't have to be in Cyberjaya. Kalau tidak, memang saya nak buat kelas langsung. So I just run for like 20 minutes to have a class with you. Right, so I'll see you Monday, inshallah. Bye-bye, take care. Assalamualaikum.